Hmm. Let's see, let's see. Zero, 1, 2, 4, 7, stuck at 7. At 10 as always I start. 9. 12. Okay, so welcome to this new episode of probabilistic robotics. Last time there were very few people. There were very few people in the lesson. I assume because of the midterm of autonomous and mobile robotics. I hope I've also seen that around 50 people had a look to the previous lesson. I will anyway at the end of this pack of slides do a small recap for those of you that did not have time to go through that pack of slides. It will be a very quick overview of what I was saying last time. Should you prefer me to do this recap now, write it on the chat. Otherwise, I will do it at the end of the lesson. Topic of today will be two core aspects of the second part of the course. First of all, how to project the uncertainty, how to recover our probabilistic view within the mechanism of least squares, and how to deal with non-Euclidean spaces. I'm still waiting for answers on the need of recap, but none is showing up, so I will proceed with the least squares and uncertainty. So, as I said, while we moved from our filtering machinery to least squares, we have been addressing only the optimization aspect. So we were using the Gaussian assumption and the probabilistic inference only to find the mean of this potential distribution over the solutions of our problem. And the aim of these 12 slides now is to figure out some statistical properties on the retrieved solution. So how accurate our solution retrieved by least square is along the different dimensions of the state. Once again, we will rely on the Gaussian assumption that is our standing pillar, and we will revise, or we will have a look at the derivation of least squares that we have given before, highlighting the probabilistic aspects. Now, you all recall that the aim of our problem, our journey in this part of the course, started with the problem of determining the maximum x, the x that maximizes this probability distribution, which is the conditional probability distribution over the measurements of the state conditioned to the measurements. So the measurements are fixed, and we are interested in finding the state which is most likely. I recall you that this z here does not have any impact on the dimension of the distribution, because this is a distribution on X, only that Z changes the shape of such a distribution. So depending on the different kind of measurements, our state might be more likely in a region or more likely in another region. So to derive least squares, we started from manipulating this conditional distribution, and the very first thing that we were doing was to apply the Bayes rule that results in this formulation over here. So P of x given z is equal to P of z given x times P of x divided by P of z. And then considering that we know nothing about x, we could just like say that it's a uniform distribution, and considering that P of z is just a number because z is a set of constant, we could say that this is proportional to the probability of x given z is proportional to the probability of P of z given x under these assumptions. Once again, we pulled out our independence assumption that resulted in the probability of all the measurements be equal to the likelihood of all the measurements be equal to the product of the likelihood of the individual measurements given the state. So said, we introduced our Gaussian assumption that bloated up in this formulation, where we had that a single measurement is normally distributed on a conditional distribution of over the potential measurement z, whose mean is affected by the state through a prediction function h, and who has an embedded covariance matrix sigma I that is attached to the measurement. This in turn becomes proportional to the exponent. We defined our error function as the difference between the prediction and the error, and basically this is equal to the exponent of the omega norm of the error. Now, again, this is a recap on least squares, which might be very useful for some of you. Embedding this exponent into the equation boils down our maximization problem into the following form. Like we want to find the maximum x, the x that maximizes this object on the right, which is the product of a bunch of exponential functions, each one with a minus in front. And the argument of the exponential function is the omega norm of the error. Now, taking the logarithm turns the product into a sum and cancels the exponent, and the minus still stays, but given that we want to find the maximum of a negated quantity, we could find the minimum of the quantity without negation, and we end up to the argument of, or the core cost function that we are minimizing with Gauss-Newton. Okay, now, having said so, the task of this lesson is to use what we have learned on the Gaussian distribution to obtain some statistics, statistics on the distribution of the x retrieved at the optimum of Gauss-Newton. You can imagine that we will be using the hammers in our toolbox, which is the chain rule to get P of x and z, so the joint distribution over the state and the measurement, and then we will condition on z. This is what we were doing in the filter, and this is what we will be doing in least squares. So, let's reason on what happens around the optimum. So the game is that I have my problem, I left my least square machinery to converge, I see that the chi-square goes down, and I have a solution. This solution is called X star. To this solution, X star, for each measurement, I will also have a prediction, which I call Z star, which is equal to the, which is obtained by taking the optimum and evaluating the prediction function at the optimum, and I get the measurement that is mostly consistent, that is predicted by that state. Now, as you might recall, in the Gaussian machinery we are forced to operate with a fine transform to preserve the Gaussianity of the distribution, and so we could describe the prediction function at the perturbation by its Taylor expansion. So basically we write down that the prediction of a measurement at the optimum plus a certain perturbation around the optimum is equal to the value of this function evaluated at the optimum, which is Zi star, plus the derivative of this function evaluated at with respect to x evaluated at the optimum. This is the derivative of the prediction. And this should sound rather familiar because it is the classical Taylor expansion. Well, recall that each measurement is attached to its own covariance matrix, or equivalently is attached to its own information matrix. So if I regard this as if I want to take the state and project it through the prediction function, I might obtain a Gaussian approximation of the measurement, the predicted measurement, around the state X star. And this is done, guess how? By using the chain rule. So we could write down that P of Zi conditioned to delta x plus x star is nothing else than a normal distribution, which is whose mean is equal to the Taylor expansion evaluated in the delta x, and it has a covariance matrix or information matrix, which is the one which was originally attached to the measurement. Is it clear? So what I'm doing is just first order error propagation. This is nothing else than, unfortunately I don't see your face, and so I don't have an idea whether you understand or not, whether I'm clear or not. Okay, so now we have described basically a conditional distribution. We have described the conditional distribution of the measurement given a perturbation actually around the optimal state. And this is in affine form. Being in affine form, we could easily calculate the joint distribution, because in order to calculate the covariance matrix of my measurement, I have to calculate the joint distribution of the measurements and the state, and then marginalize out the measurements, right? This is what I would be doing. So now I have the conditional distribution of the measurements given the state. The next step will be to calculate the joint distribution of measurements and state, which we're gonna do in the next slide. But before of that, I invite you to observe the structure of the joint distribution over not one single measurement Zi, but over the entire measurement set. So you, instead of this derivation covered the case of one single measurement. But what if my Z is not the one single measurement, but is the stack of all possible measurements that my system produces? In ICP, you could imagine this Z as the stack of all the prediction of all the points. So if I have 2D points n to the points, I would have 2n elements in this vector, because each block has, for a measurement, has dimension 2. We could easily describe this total joint distribution just by taking each measurement and taking each prediction and stacking the predictions one on top of the other. So basically, by my new mean of this total distribution Z, that I recall is the set of all, is the vector formed by all measurements, will be will have dimension of a measurement times k, where k is the number of measurements, and will have a first component which is equal to the I'm talking about the mean of this object. The first component, which is equal to the first affine form evaluated in delta x. The second component is equal to the second affine form evaluated in delta x, and so on up to the point k. Okay? And this will be my mean. Now, the mean of the entire stack of measurement. Observe that delta x is the same everywhere, because delta x is the one state that controls everything. So basically, my state will project through J along the different dimensions of my measurement space. I could then rewrite this term by highlighting the role of delta x. And so this turns out to be just the stack of Jacobians multiplied by delta x plus all the measurements at the optimum, which end up to the right. And this is quite obvious. We also recall that we were assuming that the measurements were independent. Accordingly, my omega z will be a block diagonal matrix consisting of the blocks of the omega blocks of the individual measurements, omega 1, omega 2, omega k. Okay? So this object here is the joint distribution, the conditional distribution of all the measurement given a perturbation of the state, the optimal state and the perturbation. Okay. Well, this is a joint distribution, isn't it? And then now we apply our chain rule. Once again, I invite you to have a look at the chain rule as described in the lesson where we covered the topic. In this circumstance, we will be using the formulation of the chain rule in information form. So like with the omega instead of with the sigma. But it's equivalent to the other. The one can be obtained by the other. Our task in applying the chain rule, I recall it, is to calculate the joint distribution over the state and the measurements, which will be then a vector, which will have dimensional x, the dimension of x plus the dimension of the whole measurement set z. So this is not one measurement, this is all of them. We have the ingredients, we have our conditioning distribution, P of x, which is having a mean x star and a covariance matrix, which we call sigma x, that for now we don't know. And we have a conditional distribution, which is described as an affine form in delta x, where sigma z is the one that is the inverse of omega z that we have seen before. We would like to compute the joint P of x and z. Now, applying the plane formulas on Gaussians, we obtain that the mean is equal to the stack of the state and the measurements evaluated at the optimum, because delta x is 0. So it will be just z star. And we have that omega of x and z has this particular form, where you have j transpose omega zj plus omega x plus the cross correlation terms, and finally you have the covariance matrix on the measurements, or the information matrix on the measurements. Okay. Now, I don't see the chat, so are you alive? Good. Now, applying the chain rule results in the need of putting in some assumptions or some facts. And these facts are, first of all, I know nothing about the covariance of the state. I do not have a prior in this circumstance. So if I don't have a prior, how do I express the absence that I know absolutely nothing about my my state without considering the measurements? Well, I could express it by saying that I have an infinitive covariance matrix, or alternatively and much more elegantly, I could say that I have a zero information matrix, because one is the inverse of the other. The information matrix encodes the stiffness. So, and additionally, remember that if I assume that my state at the optimum is locally approximated by a Gaussian, then the optimum itself will be the highest point of the Gaussian. And being the highest point of the Gaussian, it's the mean. Then, if I reason in delta x, I could straightforwardly say that the distribution of delta x has, of my prior delta x, as a zero mean, because delta x is the perturbation around the optimum state. So, P of delta x is basically a normal distribution with 0 as a mean, as 0 as information matrix. Then, if we want to calculate the joint distribution, in this case of P of delta x and z, well, we just like know that delta x, remember, we are at the optimum, so delta x has to be 0, and z star, which is the component of this joint distribution, has to be the predicted measurement. And I will also have a certain covariance term, which is what I'm interested in, which will be the joint covariance term, which is the joint covariance over delta x and z, or x and z. Okay, now, okay, excellent. Now, let's go back a second. Look at this formula over here. Looked at it, and look at this formula over here. The difference between the two is just that here I do not have omega x, because omega x I set it to 0. Okay? Well, this is cool, because this is the joint information matrix of the measurements and the state. What I've done here with respect to this case over here, I highlighted the role of delta x, right? So delta x is my new variable. Instead of calculating something in x, I calculate something in delta x, because both quantities are related just by a simple minus. So if I want to think about the distribution in delta x, this distribution will have the very same shape as the distribution in x, only that it will be shifted so that its mean is 0. This is quite interesting, because this sounds familiar. It should sound familiar, because this term over here is a part of the least square algorithm. Now, if I have a joint distribution having this information form, and if I want to condition on a specific measurement, what will be the information matrix of the variable after conditioning? Well, will be just the block. Will be just, in this case, this is the information matrix of the state, will be just sigma xx, which turns out to be equal to J transpose omega z J. So how do you reach this consideration? Well, let's first have a look at what it means J transpose omega z J. We go back and we retrieve our definition of this gigantic Jacobian, which is the one constructed by stacking all the Jacobian of the measurements. J, as we recall, is the stack of all input Jacobian of the measurements. Omega is the diagonal matrix constructed, the diagonal block matrix constructed by accumulating the blocks of the measurements. And this is the transpose of this. Now, if I do this product, well, this will be equal to this object multiplied by this, summed by this object multiplied by this, and so on and so forth. So this is equal to the sum of all the tiny little H matrices that we were finding in our least squares. But what is it? What is this sum? Well, this sum is nothing else than the H matrix that is calculated by least squares. Okay. Then we are quite set, because we discovered how to compute this term over here. And then we proceed. Remember that we don't have this, and we have this. We don't have the cross-correlation terms yet. But we were able to calculate this object. Do we need the other terms? Who knows? Let's look at what do we need for doing conditioning. We have a joint distribution over state and measurements, and we want to calculate the conditional distribution given the actual measurements. Looking at our rules on conditioning, we figure out that the new conditional distribution is a Gaussian that has parameters x, that has parameters ni of x given z, where this is the information vector, which is equal to the information matrix times the mean, and has a certain information matrix omega of x given z. This object here will have the dimension of x, clearly. The rule on conditioning tells me that the condition in the information vector is equal to the original component of the information vector on x, which is to which you subtract the cross information matrix multiplied by the conditioning measurement. And more importantly, tells me that omega of x given z, so the uncertainty of my conditioned state, is equal to omega xx. But omega xx is exactly what we calculated one slide ago, which is equal to h to the minus 1. To h. Sigma is equal to h to the minus 1. Then, well, we're done. Well, basically, yes. But how does this all come together? Well, if we wrap the things, we look after the other rule of conditioning, so the rule of conditioning in covariance form, so with the moment parameterization, you figure out that the conditioned mean is equal to the mean at the optimum, which will be x star, multiplied by a correction term that depends on how different are my measurements from the predicted measurement. But I'm at the optimum, so I can assume that my measurements are very close to the predicted measurement. Plus I have these two matrices here that massage the correction and presumably leverage the contribution of z minus z star to bring it to 0. So I could say that, but intuitively, if I am at the optimum, I am in this condition here, where z and z star are more or less, so the actual measurement and the predicted measurement are close. Accordingly, my mean will be just at the will be equal to the optimal mean that I found, but this is also a geometric, you can understand it just by looking at the fact that the minimization brings you in the highest point of the Gaussian, and so that one has to be the mean. And more importantly, the covariance matrix of my estimate is equal to the inverse of the H matrix, which is the approximated Hessian. And yeah, and with this, you could actually tell how certain you are of a covariance matrix, how certain you are on the solution reported by ICP or by a generic least square algorithm. Some considerations are that this derivation tells you also how many measurements at minimum you need to find a solution. Because, well, if I have a measurement which has dimension 1 and I have a state which has dimension 10, well, each time I integrate a measurement in my machinery, I add to the H matrix a contribution which is in the form j omega j. But if j, in this case, will be 1 times 10, if I have a matrix which is 1 times 10 multiplied by a matrix which is 1 by 1, so which is in this case 10 by 1 because it's transposed, multiplied by a matrix which is 1 by 1 because this is the size of the measurement, and multiplied by a matrix which is 10 by 1, I get a matrix which is 10 by 10, which is consistent with the dimension of H. At the same time, I know that the rank of the contribution of this term will have rank 1. So one measurement, in the best of the cases, if I have a one-dimensional measurement, this will qualify only one dimension of my H matrix. And assuming that the measurements are all different and they all stimulate different components of the state, or they all highlight, observe different components of the state, at minimum I would need, in this specific case, 10 measurements to be able to resolve the state. At the same time, if I don't have an H matrix which is positive definite, which means that I cannot resolve the system, I also know that along the dimension of the H matrix where it's not positive definite, which means that the null space of the H matrix will identify the subspace of my state that I cannot determine with that particular set of measurements. But this is not sufficient. This is only a necessary condition. So at least I need to have a number of measurements whose dimension is equal to a number of measurements where the sum of dimensions is equal to the dimension of the state. So if I have measurements of dimension 2 and I have state of dimension 10, I need at least to have 10 measurements. 5 measurements, no? 2, 10. Because each measurement will provide me a rank contribution of 2. But this is a minimum condition. right? Because there are circumstances where through the Jacobian or through the measurement function I cannot absolutely observe a component of the state. This was, for instance, the case when I was doing the example on range-only registration, like where we had a set of points, and we were only able to observe with our robot the distance from these points. In this case, the theta component was completely irrelevant to my prediction, because if I stand in one position and there is another object at a certain distance and I rotate in this position, well, I rotate around myself, the range measurement towards that object does not change at all. So the theta will not be observable. And I will realize that because I will figure out that the Jacobian will not stimulate, in the end, will not be impacted by the theta component, which means that the Jacobian will have dimension 2, all Jacobians, so rank 2, all Jacobians, so rank 1, all Jacobians will have rank 1, but the maximum that I can observe by stacking together the H matrices is a subspace of dimension 2 of my state if I also consider the angles. Okay? Similarly, in case you have 3 points, so how many points at minimum you need to resolve ICP in 3D? The one that we have seen last time. By doing the simplistic, let's say this way, calculation, you say, okay, each point is a measurement that gives me that has dimension 3, right, in the space. Each point has dimension 3. My state has dimension 6, right, in case I'm interested in finding the rotation and translation in the space, because I have 3 components for the translation and 3 components for the rotation. So you say, okay, by doing the analysis of the problem, I need at least 2 measurements, but at least. But this is not a sufficient condition. I need at least 2 measurements, because with 2 points, I, in theory, could observe 2 measurements, because with 2 points I could observe, I could potentially have a rank increase of 6. Each point gives me 3. Okay, but this doesn't really work, because if you do so, you will find that your H matrix is rank deficient. So if you only take 2 points, the H matrix is rank deficient because of how the functions, the error functions are constructed. And why is it rank deficient? Well, just like think at what happens if you try to register 2 points. I have 2 points here, and then I match perfectly these 2 points with other 2 points here, which are observed from this position. Well, this gives me still a degree of freedom along a circle, basically, which is obtained by matching the 2 points that I have, but then still I have an undetermination in a circle whose axis is it's like in a disk, in a circle that lies on a plane whose normal vector has the same direction of the two of the 2 points. No, so this is the vector where the hypothetic circle falls, and then my point like moves. My solution moves in this direction. Yes, and to your feeling, which space where my covariance matrix will be undetermined? Well, remember that the covariance matrix has to describe a linear subspace, like the null rank, the null space of H will have to be, in this case, a line. In fact, the uncertainty is on a circle, but we are operating with matrices, and if I tell you to calculate the null space of a matrix, well, then it's going to be either a direction, so a vector, or a plane, or a hyperplane, but it's not going to be a circle. Okay, and then here comes the limit of our linear assumption. What will happen is basically, depending on the minimum found, depending on the actual minimum, you will find if you dump the system and do something in order to get a solution, you will find that the subspace is tangent to the circle where the solution is. But overall, when you have a null space in H, it's never a good idea. Okay? Conversely, if I put 3 points, well, with 3 points I might be happy. But actually, this is not even, if I have 3 points in ICP, I would be able to find a solution. And this, you can understand it just by thinking about the geometric consideration. Like, just think about the mechanics of the problem. I have 1 point, I have another point, I have a third point. Okay, I'm locked. I'm rigidly fixed in this location. Another aspect that might be of interest is is it true that I really need 3 points, or might I need something less? I give you a hint. In order to fully determine ICP, actually, I might need 2 points, because this is the minimum, and I might need another information coming from a third point, which must not be necessary it's all 3 coordinates. Might be only that I am able to observe just 1 coordinate of the third point. By using this covariance propagation, in the end, or reasoning, the message of the lesson is that you are able to figure out how accurate is your solution. And then we are back in the first word, or the first word that appears in the course name, which is probabilistic. Okay, so this concludes the first pack of slides, and then let me move to the second block, which is the manifolds. I mean, traditionally, now I see that I have 15 concurrent viewers. Traditionally, this is the point of the course where the class halves. I don't know if because AMR has been given. I hope, by the way, that what you have learned in filtering was turning out to be useful for doing the test of AMR. But I only have 14 people. Last time they were around 20, so there has been a loss. Now, let's go to the second part, which will be accompanying us basically until the end, until the quasi-end. And let's talk about least squares on non-Euclidean spaces. So, let's start with something you are very familiar with. In robotics, you often encounter spaces, domains, which are anything but Euclidean. Like Euclidean means something, some space that you can map to Rn, and then you can measure the distances consistently with the Euclidean norm. a classical space that do not have an Euclidean, an example of an Euclidean topology might be a line, might be a plane, might also be a finite surface like this piece of paper, right? If infinitively extended, as long as it doesn't wrap. A classical example of non-Euclidean space is the rotations. Normally we deal with 2D angles, no? Angles in 2D. And if we look at the topology of the angles, we have learned also from analysis 1, I think, that they can be seen in the complex plane, right? Because the Euler formula. Angles are homotopic to a circle, so they have the same topology of a circle. Because, well, if I want to measure the distance between a point and another, well, I could measure between an angle and another, I could measure the distance just by walking along a unit circle and walking, for instance, from a point to the other, and then by counting the steps, I figure out how far I was. But this is a manifold or a non-Euclidean topology that has dimension 1. The Euclidean topology that has dimension 1 that we all know is the line. Normally we take angles and we measure the differences just like without thinking. We take these angles, we map them into a line, this is what we do, and then once I ask you, hey, what is the difference between two angles? Well, you take an angle, for instance x0, you take another angle x1, and then in order to calculate this distance, you go back to a line, you find where is the point x0, you find where is the point x1, and you calculate the difference. This is what we all do, right? Because we calculate the difference using the normal algebra of lines, which is Euclidean. Is this correct? Well, as long as you are away from the end of our mapping, this could work. But there is another circumstance where basically calculating the distance along this segment, so repeating the procedure, leads to the wrong result. So let's say that I want to calculate the distance between these 2 points. Well, if I repeat the process, I find that x0 is here, x1 is here, and then I find that the distance, in order to move from x0 to x1, I have to walk along all this path, right? But this is definitely not the minimum distance between x0 and x1. Because the minimum distance will have the opposite direction. So I will have to say, I have to move, instead of from here to here, I will have to move from here to here, following this part. Now, this seems trivial and not necessary when I'm talking about the 2D machinery and the 2D angles, but turns out to be quite relevant when we move in 3D, because there the normalizations are held, and we have to be careful in measuring the distances in an appropriate manner. So, what could we do to have a general mechanism that no matter on the topology of our space, could be a circle, could be a sphere, could be a torus, no matter on the shape of our surface, and no matter of how we sit, it will give us reasonably good results, or it will not present all the problems that we encounter when we do this brutal mapping from circle to segments. Okay? Well, what could you do mechanically? Invent a procedure that solves this problem, at least for the circle, once and forever. Well, an algorithm, let's say this way. So our task is, I give you 2 points on the circle, and you have to tell me the correct distance between these 2 points. Okay. Think about a circle, but also think about a sphere, right? You have to tell me the correct distance on the sphere. And well, in case of a circle, one could say, okay, I calculate the difference of the points and I normalize. Okay, that works for the circles, so works for the 2D angles, but it's not very flexible and it's not very general. Alternatively, a generic machinery would be the following. I want to measure the distance between this point and this point. So, at the beginning, when I was constructing my Euclidean mapping of my circle, I decided that the origin of my mapping was the 0 point, was the 0 angle, right? Choosing the 0 angle as the origin of my mapping caused the existence of the loss of validity of my Euclidean mapping basically around pi, no? Because this is the point where I have to cut the circle to morph it into a line, and whenever I cut, basically I lose the possibility of calculating distances along that the path that I've cut. So an idea of this generic procedure would be, you know what? No one told me that my mapping has to start in the origin. I could make my Euclidean mapping starting from the point from which I want to measure the distances. So I could make my mapping starting from x0. So what if in my mapping here, I define that the origin of my mapping is not this point, but is this point over here. And then I end up to this situation. So this 0 point here maps on x0 on the manifold. Okay? In this way, basically, I have moved the singularities far away from the point where I'm calculating the distance. Having done this trivial mapping, so basically I say my chart is, this is called a chart, which is an Euclidean mapping constructed around a specific point of the manifold, whose origin is the point of the manifold where we constructed the mapping. So 0 in the chart matches to x0 on the manifold. In this lesson, we will use capital letters to denote points on the manifold, and we will use small letters to denote points on the chart. And here it's like just to show the mapping. If we do this, well, we are quite happy because we can calculate the distances from x0 quite resiliently in this case, because the singularity is far away. So the mechanic is then the following. When I want to calculate the distance, I know that I can calculate the distance only on an Euclidean subspace, right? On an Euclidean mapping of my space. I call this Euclidean mapping, which is a line or a plane or a cube. I call this Euclidean mapping a chart. But I can calculate the chart in any point of the manifold. And calculating a chart, which is this, corresponds to have a new origin in the chart, which is centered in the point where we calculated the chart. Now you could think about the same in a sphere. You could repeat this very same process on a sphere. Because if you have a sphere, well, you could always choose, and you want to measure the distance on a sphere, you could always choose a point on the sphere, and on this point you could fit a tangent plane, right? This would be an option. And this tangent plane will be the chart around x0, around the point that you choose to linearize. And then when you want to measure the distance of the points along the sphere, well, you will do the mapping on this plane. Or even better, instead of using a plane, you could use a hemisphere. Now you could just like construct a local mapping just by slicing the sphere around the you cut it in half in a way that the most distant point of the half is the point where you measured where you constructed the sphere, like half a soccer ball. Okay. Now, can we describe this mechanism in a little bit? This lesson is a little bit abstract, but then it nails down. Can we describe this mechanism in a little bit fancy form? Yes, through a formalism brought back by these three people some years ago. Our task is to compute the differences, right? So on a generic manifold. For now, we assume that we have a machinery that, given a point on the manifold, like given this point over here, returns us a function that, a mapping that, such that the origin of the mapping 0 corresponds to x with 0, and then all other points are mapped accordingly. So this will be x0 plus delta x, x0 plus something, blah, 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 and so on and so forth. And each of those corresponds to one element. So there is a mapping between each point here and each point here and back. But the important thing is that this is Euclidean, and the origin of this line or plane or whatever is x0. Now, let's assume our task now is to compute the differences and to formalize this mechanism. My goal is that I do have 2 points on this manifold, a point x0 and a point x1. Imagine these points on a sphere or on a circle. And what I want to compute, like in red, is the difference on the chart. I recall you that the difference in this case was just a number, but in case the manifold is two-dimensional, like in a sphere, the difference could be a delta, could be a 2D vector, okay? That tells you how to move from one point to the other. So, the mechanism says, compute a chart around x0. We are on our circle, on our sphere, we construct an Euclidean mapping between x0 and all nearby points, such that a point in the mapping corresponds to a point on the manifold, and the 0 point on the mapping corresponds to x0. Then given this mapping, we calculate the location of the other point, the point from which we want to measure the distance, or the difference, which is x1. We have detected this other point. Then at this point, we have 2 elements, 2 points in the chart, right? But the chart is Euclidean. And so we could compute the delta x, the difference, just by taking this, the mapping of x1 on the chart, because the other one we know it to be 0. And this will be the difference on the chart. We could wrap this operation, this algorithm, take the starting point, calculate the chart, localize the second point in the chart, and calculate the Euclidean difference on the chart by defining a so-called operator that we call box minus. This is the difference between x1 and x0. This means go to x0, construct a chart, localize x1 on the chart constructed in x0, and then take x1 and see how far is x1 from the origin of the chart. And this element returns you delta x. Okay? Now, if we can compute the difference, we can also apply the difference. And so, applying the difference is the other way around. We can undo this process. So, if I give you a starting point and on the manifold, and I give you a difference on the chart, it's equivalent, like imagine that you are on an Earth, which is a ball, but despite not everyone believes so. You are on a point on the Earth, let's say in Oslo, and you buy a map in Oslo, and you, looking at the map, you would like, which is a flat, right? You would like to go to Rome, maybe, right? So like you look into the map the direction from Oslo to Rome, which will be probably Oslo-centric, the map constructed in Oslo, right? Because where the origin of my chart will be in Oslo, and everything else will be far away from this origin, right? So like I'm in Oslo, I buy this chart, and then I study the path to Rome on the map. I localize Rome on the chart, and then I map this point on the chart, which is Rome, into the real Rome. So it's like I walk on the chart, but while walking on the chart, I find myself on a point in the manifold. So the process is that I go to my starting point, I get a chart in my starting point, then I calculate the difference, I apply this perturbation vector, this motion on the chart, and then I wake up in another location on the chart and I map it back to the manifold, to the position. It's like basically the reverse of the other process. We can, for symmetry, encapsulate this piece of program. So take a point, buy the chart, calculate the difference on the chart, figure out where you are in the chart, go back on the manifold, by an operator that we call box plus, that takes two arguments. One argument is a point in the manifold, and the other argument, small delta x, is an Euclidean perturbation on the chart. This means that if you move of delta x from x0 on the chart, you end up in x1, which is a point in the manifold. Okay? Now, we will immediately see how this could come in handy. What you might sense is that operating on the charts results in being away from singularities that might give pain. Now we have seen very, very small problems like ICP or whatever, where points where we have a lot of measurements and the state that it's rather small. In this case, well, might be that the singularities don't hurt you that much, but there are also circumstances where they do. But in the generic case that we will address when we have thousands of variables, well, the singularities will play an important role. So singularities are evil, and manifolds is a way to simply deal with them. Now, how do we embed our machinery into the least square infrastructure? We first recap the original formulation of least squares that should be familiar to everyone, and then we reason on how we can modify these Euclidean least squares to embed our newly acquired notions on the manifold. Okay? Well, I'm really dry. I will have to, after a couple of slides, I will call a break of 5 minutes. We have our standard Euclidean least squares that was process starts by clearing H, clearing B, our two matrices, and then for each measurement we calculate the error, we calculate the Jacobian. Importantly, the Jacobian is obtained, both error and Jacobians are obtained by evaluating the prediction and the Jacobian at the current optimum x star, and then we calculate our contribution of the H matrix and the B vector, and then we calculate the perturbation over the state that would make our quadratic approximation better by solving this linear system, and we apply finally this perturbation. Now, having introduced, remember that in order to solve a linear system, delta x should be Euclidean, right? And I will tell you more. In order to construct the linear system, E should be Euclidean. How to apply our least square machinery to this new manifold concept? Well, the straightforward approach would be, okay, well, whenever I have a minus, I subtract it with box minus, beside in this case over here where I am summing matrices. and whenever I have a plus, I subtract it with box plus. Almost. Now, imagine that now everything has become Euclidean, right? Everything has become a manifold, so both x and z. The very first thing that we could do is to say, okay, all right, now I have my error. My error should be Euclidean, and given that my prediction might not be Euclidean, nor my error might be, my measurement might be Euclidean, I might just, well, calculate the error vector by applying the box minus. Remember that in the definition of chart, this means like construct the chart around Zi, evaluate Hi on the chart, like figure out where Hi is on the chart, and then calculate the Euclidean difference on the chart between the origin, which is in Zi, and the projection of Hi through the chart calculated in Zi, right? This is what this means, and this is the result of this is Euclidean. So the very first thing we could do is to calculate a fantastic Euclidean difference, right? I recall you that in case the spaces are Euclidean, the box minus degenerates to a standard minus. There's nothing new with that, right? Because why do I need to do all this work if in the end I'm already on the chart, in case I am Euclidean? So this sounds logical, I hope. Then a tricky point is the Taylor expansion, right? So remember that in order to calculate our quadratic form, we had to take the error function and express it at the perturbation. So calculate its Taylor expansion around, like, starting from a linearization point and around a certain applying a certain perturbation delta x. Now it's quite tricky because in doing this work on the manifold, we calculate a linearization point x that always lies on the manifold, right? At the same time, when we calculate our quadratic approximation and then thus our Taylor expansion, we are expressing basically this formula as a certain term plus another term which is multiplied by a perturbation delta x. Okay? But if I would derive this with respect to x, the things wouldn't work. First of all, because x is a manifold. It might be a rotation matrix, might be an arbitrary object. Actually, I might not be able to carry on this operation, right? But what I can think about is to consider the following fact. Within one iteration, one single iteration, right? The linearization point, so the origin of my chart, stays fixed. I hope you see that. The origin of my chart doesn't move within one iteration, within one round. So I could just regard this capital X here, given that it does not move, as if it was a constant. And then I could conduct my derivation, so the derivation meaning differentiation, by considering delta x as my active variable. So this function over here becomes not anymore a function in x, box plus delta x, but becomes nothing else than a function in delta x where capital X stayed fixed. So you could imagine it as if you would delete this capital X here and put a big X here, EI capital X of delta X. Okay? Now, doing so will give us a Taylor expansion, and then if we want to express our perturbation, how this value, this number here, changes as a different variation in delta X, we could derive with respect to delta X itself. Where do we put this delta X? We evaluate this delta X in 0, because 0 we know it to be the origin of our chart. So this object over here denotes how much the error changes if I move around the linearization point on the chart delta X of a certain perturbation delta X. Okay? This is an Euclidean object. So I just derive with respect to this function. And where do I derive? I recall you that before we were deriving in X. No? Before our derivative was evaluated at the current optimum. In this case, the derivative is calculated at the current optimum, right? Is calculated at the current optimum because X stays constant, but the current optimum is where delta X is equal to 0. Because if delta X is equal to 0, I don't move from the optimum. So, this becomes my new Jacobian that expresses how a variation on the chart influences my error, but after going through the mechanism of the box plus. Okay? And I will call this object over here my new Jacobian Ji, and this is the constant term, which is the error function evaluated at the optimum. Okay? This is the most important thing. You have to derive with respect to delta X evaluated in 0. Of course, this should be called delta X prime just to differentiate it from this, but yeah. Abuse of notation. That's after the end, the other aspect of my algorithm that is relevant, is like after the end, I do all my machinery and I will get a solution. I will get a solution in which space? In the space of the manifold? No. I will get a solution in the space of the chart. So for each component of the state, or in my state, I get a perturbation vector in the chart. So, and then I cannot apply this perturbation vector straight away to the point in the manifold, because one, let's say, is a rotation matrix, the other one is an angle. I can't do that. I have to first lift it. So apply this perturbation by using the coherent box plus operator. So at the end, I will have to calculate the new optimum by taking the old optimum and applying the perturbation delta X to the old optimum. Having done that, we can end up, let's say this way, to the first implementation of least squares on the manifold, which is exactly the same as before, with only one difference, which is basically that the Jacobian is calculated, two differences, that the Jacobian is calculated by differentiating the error function box plused with delta X in delta X evaluated to 0. And at the end, we will obtain a vector of perturbations that we need to apply to the previous optimum by using the box plus operator. Okay? Now, to have a grip of this, just think that X is a 3D transformation matrix and delta X is a 6D perturbation vector of the transformations. This operator over here, so X star box plus delta X, would mean take a transformation matrix and move and consider it as an origin, and move from this origin of a transformation which is expressed by delta x. So this x, capital X, does not need to be Euclidean. Could be a data structure, could be a matrix, could be whatever you want. What needs to be a real vector is just delta x. Okay? Then we see, so this is in the end manifold with least squares. Now I will wrap up the methodology, then I'm getting completely dehydrated, so I will have 5 minutes break. I will stop the live and then restart the live, or maybe leave the live on, and to prevent connection issues. First I wrap up the methodology that we will have to follow. Basically, this is exercise 2 of probabilistic robotics. Okay, so learn this methodology, like become familiar with it, because if you use it correctly, you have a powerful weapon that will allow you to formalize and to address very complicated problems. Now, the methodology starts from that you are presented a problem and you are asked to solve it with least squares. Not necessarily. Sometimes you figure out that the problem can be solved with least square by yourself, and this is actually what I would love to for you. But you start, and the first thing that you do is to qualify the state space. Now, in the qualification of the state space, you have to tell what that space truly is, not how you represent it. Okay? So, whenever we are talking about transformations in 3D, these are transformations in 3D. They belong to the space of SE3, right? If we're talking about lines, also another example could be a line fitting, right? Or slam with lines, or you want to estimate a set of a curve, a parabola, whatever you want to estimate, a plane, let's say this way. You're asked to estimate a plane. The plane, the domain of the planes is not Euclidean, right? Because how do you represent a plane? Okay, you can represent it with a normal, right? And you could represent a plane just by a vector that goes from the origin to the minimal plane, but this leaves undetermined all the plane that pass through the origin, because in this case all the vectors that are zero will describe all possible planes, so that doesn't work. So you could represent a plane with a normal vector to the plane and a distance of the plane to the origin. Then you have 4 coordinates, right? You have 4 coordinates, but the normal is constrained to lie on a unit sphere. So again, you are on a unit sphere. The sphere is a non-Euclidean domain. So, well, you have to qualify the domain, and the domain might be also the cross product of domains, right? Like, for instance, in case of a plane, you could talk about a plane potential way. You could represent it as a, well, first of all, it's in the domain of the planes, but you could represent it as a normal vector, right? And the distance from the plane, and this is 4 components, right? Then you have to define an Euclidean parameterization for the perturbation. Now, after you qualify the domain, you have to say, okay, now I have this object. Let's imagine that I have this plane, which is represented by a unit vector, like a unit vector representing a normal and a distance. Now, in order to find an Euclidean parameterization, you could think about minimal motions. How could I move a plane in order to bring it everywhere I want in the space? And then you could define, I don't know, you could move it along the azimuth. So you could rotate the plane along this direction, you could rotate the plane along this direction, and you could shift the plane along the norm vector, right? Are these 3 operations sufficient to move the plane wherever I want. Yes, no, this might be an Euclidean parameterization for the perturbation on a plane that is dimension 3. But you are left free to choose which Euclidean parameterization you can define. The only thing is that this perturbation should be minimal. And then after you have defined what an object of the domain is and how to move it, you can define a box plus operator, which is nothing else than a procedure to move this object, to apply these minimal motions to this object in the space, in the domain. Then the second, then we go to the measurement space. Once again, remember that the measurement space could be a complicated thing, could involve transformations and whatever. First of all, you qualify the domain, same as you have done for the state space. Then you define an Euclidean parameterization for the perturbation, so how an object of this domain can be moved, right? And then you define a box minus operator. So like, given two objects of this domain, how do I determine the set of minimal motions that bring one onto the other? After you have qualified the domain, then it's quite straightforward to identify the prediction functions that are those that produce the measurements given the knowledge of the state, and then you can define the error functions equivalently. Okay? Now I'm completely dehydrated. If you have, I will leave the video running. Now it's 22. I mean, now it's my clock signs 22, 11:22. I would say we have an 8 minutes break, and we come back at 11:30. Okay, I will not switch off the connection because then OBS gives issues and so on and so forth. So, if you have questions, please write them in the chat, and then we will see examples, and we will transform all this fluffy thing into something which is more concrete. So see you in 5 minutes. I go to drink and get a coffee. Okay. All right. So, I mean, so as an example, obviously, we will dig through the well-known ICPs. Like, why are you so fixed with ICP? Because I believe that providing the same problem makes you familiar with okay. Will result in being quite familiar. So showing a problem that you know well and showing the different aspects of this problem and using it as an example repeatedly helps you concentrating on the concept. But I remind you that this course is not on ICP, and it's not only on ICP. ICP is just one instance of the many problems that we will be encountering. We will map the stars, we will do fancy things, but the first example on the manifolds has to be simple. Now, from what I read from the chat, I also realize that it's well seen if I give you a quick introduction of the lesson of last time, which actually turns out to be not so coupled with this one. So it's not dramatic if you don't didn't see it yet, but just to help you to follow the slides better. Okay, so let's restart. We start from the famous ICP, huh? And so like ICP into D. ICP into D is, we have a set of points. We know where these points are. Okay? Well, I made these slides once, I'm reselling it over and over. We have a set of 2D measurements in the robot frame. And these are measurements in the robot frame. And what we want to do is we know the correspondence. So we know which point in the word corresponds to which point sensed by the robot. Okay? And what we want to do is to find the transformation that register the 2 point sets, basically, so that minimizes the prediction, the difference between the prediction and the observations in the points of the words and in the points measured by the robot. Okay? Like basically we want to register these 2 point sets. But we have seen, and I hope you remember, that that we could approach the registration problem also with underqualified measurements, as we have done with bearing only measurements, and we have done it in a lesson in the past that I invite you to have a look at. Okay, we could also, now that we have the machinery, decide to register a set of lines. Imagine that we have a set of lines in the word, a set of lines sensed by the robot through a famous line sensor, and then we would like to figure out a registration between the two. Okay. A cool problem would be, just now that I'm thinking, imagine that you have an edge detector on an image, right? And you have a wireframe model of the scene. And running an edge detector and some line extraction, you figure out the lines into the edges extracted from the image, and then you might want to register the lines in the model with the lines that you detected from the image. This is projective line registration. This could be. This is in the same class of this could be easily an exercise of example. Of course, we will see also vision. We will see other things like a little bit, so that you are equipped to carry on these tasks. Now, we will now rigidly follow the methodology of the other slide. That normally I put it on the blackboard. Now I have only one single slide, so I can't put it on the blackboard. No. I can't put it on the blackboard, but yeah. The very first thing that we do is to qualify the state space, right, of this problem. Now, we have to go all the way around, right? We have to decide or to identify what is our state. In this case, our state is very simple because it consists of an object that we know very well, is an element of SE2. And we can decide to represent it as we want, because I recall you that this capital X in the manifold can be an over-parameterization of your state. Okay, can be something which is convenient. And then when dealing with transformations, I mean, everyone has his flavor, but what I really like is to think about transformation matrices, because they are easy, you can multiply them. Yeah, they might lose conditioning if you multiply them too often, numerically I'm talking about, but this is the most plain object. It's just a matrix, and you're happy with it. You don't have singularities. I like rotation matrices, okay? Transformation matrices. So we represent an SE2 object through this object here that you should be more than familiar from Robotics 1, I think. If you're not familiar, please ping me on the chat. But, well. Then we represent a perturbation. Well, a perturbation is a way to change a transformation matrix. And in a plane, you can translate it and you can rotate it. So you have three components. And we call this Euclidean parameterization of the chart. So our chart will be delta x, delta y, and delta theta, which is a locally Euclidean space, right? Okay. Now we have these two items. We have a transformation matrix. We have a perturbation vector. And then we have to invent a way to apply this perturbation to this matrix. We can really do what we want in this case. Okay, there are better and worse things, but the only thing that we have to remember is that if the perturbation is zero, applying this perturbation to this object must leave the object where it is. So if I buy a chart in Oslo and I don't move from Oslo, then I stay in Oslo. Okay? And then what could you do? Well, now you will encounter the famous V2T. The most sensible thing to do is to calculate a tiny transformation matrix from the perturbation, which we do with the well-known V2T operator, no? That takes the rotational component and computes the rotation matrix, takes the translational component and computes the translation vector, and then we are left with what I call capital delta X, which is another fancy, nice, well-behaved rotation matrix, right? A transformation matrix. Okay. Then, if this is zero, this becomes the identity. So the condition for the manifold is satisfied, for the perturbation is satisfied, because then the next step will be to multiply this perturbation to the original matrix. Here I use the left multiplication. I could also define the box plus by taking this object over here and multiplying it to the right. Okay? Both are legit. The construction of the box plus operator is left to you. It's consistent as long as this is minimal, and if this is zero, the box plus operator should, if delta x is zero, the box plus operator leaves x in zero. I just choose this way to parameterize to construct the box plus. I recall you could also define x plus box plus delta x as capital X multiplied by V2T delta X. So inverting these two factors. Okay? Well, I just choose the definition because I know, now having done all derivation in the front, in the back, and so on and so forth, because it results in a lightweight calculation for the derivatives. Then I'm not done. Well, then I'm done with the state because I have fully defined the qualified the domain, defined the perturbation, and defined my box plus operator. Here there is my fantasy needed. Okay. Need to have breakfast. The belly is grumbling. So other aspect was define the measurements. Well, in this case, the measurements of this version of ICP are Euclidean, right? So if they are Euclidean, then automatically you don't need to define the box minus, you don't need to define the Euclidean parameterization because you already live in an Euclidean parameterization. You are as happy as you can be. The prediction function then becomes the same prediction function of ICP. I recall that the transformation we are estimating is the transformation that maps the word in the robot frame. So in order to have the prediction of the point, we take this point, we rotate it by r and we shift it by t, which we could, with an abuse of notation, write it as capital X multiplied by pi. If this should be consistent, this pi should be a homogeneous point having a 1 at the last component, but we live happily with this abuse. Okay. If the box minus operator is not defined, does not need to be defined in the measurements, we are in the happy situation where the derivative of the prediction function is equal to the derivative of the error function, and so we just derive the prediction function. But anyway, the prediction function, okay, we just derived the prediction function. I recall that we have to express the prediction function by adding the perturbation, because what we will be doing in the next slide is to derive with respect to the perturbation, having evaluated the perturbation in delta x equal to 0 and having locked the capital X to the current optimum. So if we expand our definition of box plus inside the H, well, before it was x times p, then it becomes x box plus delta x times p. Okay, we once again expand box plus and we find our definition of V2T, which is V2T of delta x, which multiplies x times pi. So why that? Look at this formula over here, this block over here. Go back, look at this block over here and this block over here. It's like we're just taking this and replacing instead of this, and we have V2T of delta x times x pi. Okay. I recall that capital X, which is my state at the optimum, does not incur in the derivation, so I do not have leaving the components of x into my formula. So then it's completely reasonable that I absorb this x times pi into another thing that I called p tilde with I. Okay? Which is just like pi multiplied by x. According to this thing. So it's rpi plus t is p tilde I. Then, well, then I expand, so to say, the definition of V2T. So if I have to, V2T is a transformation matrix, right? Like this object here is transformation matrix, was rotation matrix is R of delta theta, and was translation vector is delta t. So if I have to calculate this, then this ends up in R delta theta times P tilde with I plus delta t, just by applying the definition of V to t. Okay? And I ended up with the prediction function that I'm going to derive with respect to what? With respect to delta t and delta theta, which are the components of delta x. So, let's proceed. The derivative of this object over here will be an object which is tall 3, because the h as a is tall 3, and it's wide as much as the state, and the state or the perturbation, and the perturbation is delta x, which has dimension 3. So this object here will be 2 by 3. Now the derivative of this object with respect to delta t is quite trivial, right? So here I will have a 2 by 2 block, which is this thing derived by delta t, which is in a cool way will be the identity 2 by 2. And then this object over here will be a vector, because otherwise everything couldn't be 2 by 3. And this vector is equal to the derivative of this object here with respect to delta theta, evaluated in 0. All evaluated in 0. R prime of delta theta is cosinus sinus minus sinus cosinus. Evaluated in 0 is 0. The derivative. The derivative will become then minus sinus cosinus minus cosinus sinus. This will be R prime. Evaluated in 0 will be 0, 1 minus 1, 0. Multiplied by pi. So if I do this multiplication, I end up with this fantastic vector over here, which is minus p tilde with I y minus p tilde with I x. This is a skew-symmetric matrix, right? Minus a skew-symmetric matrix. We will find something very familiar when we will lift the problem to 3D. Okay. Cool. Then there's not much we have to do. We just run and build our Octave program that calculates the error and the Jacobian. Like it's just a one-to-one transposition of what we have seen before. This function takes x, which is my transform this time. So it's a rotation transformation matrix, takes a point and takes a measurement, calculates the prediction, calculates the error, and calculates the Jacobian according to these equations over here. So in the first two blocks you find the identity, and in the last column you find z hat is my p prime, p tilde. You find minus z hat the y component and z hat the x component. A ICP version, the manifold is exactly the same as before, the manifold version of the least square iteration, with one single difference. Who spots the difference? Well, I don't know how long the latency is. In the previous slide, we were seeing a plus here. Now we see the box plus. So we have to take, at the end of the Giostra, at the end of the, I don't know, the accumulation, we will solve our linear system as we were used to do, and we will have then a perturbation on the chart that we need to apply to the previous solution. And then we are done. Now comes the time that I have to show you that this program really works, but mostly I realize that these programming spots are necessary so that you are aware that you have something in the repository. Otherwise, stuff appears and you don't know what do you need to do with it. This is the exactly the same program that we encountered before. This is the piece of program that you have in the slides, and what you see here is the test for ICP that generates a set of random points, applies the transform, and runs the iteration on ICP on the manifold. Quickly. And then key evolution. Let's say I give it 100 points, I give it a target transform of 10 minus 20 and pi divided by 2, so 90 degrees, and number of iterations, I would say 10. Okay, and this is the result. So you see that it goes down quite quickly. Now, wasn't that hard? The machinery is quite straightforward. The only thing that the only time that one has to pay attention is in qualifying the domain and defining these perturbations. As a possible exercise, you might you might think of changing this ICP formulation and modifying the program that I proposed you with the bearing business. I think it's here. Yeah. ICP2D.m. Oh yes, there was a bearing version of the exercise that I proposed you, and you might want to use this manifold machinery to see and to do your first practice, your first manifold version of ICP on a different problem. Okay? So, you have two pieces, you have just to put them together for now. But I will not develop the exercise because I would like you to try. It takes you approximately 15 minutes, but it will take you 1 hour because you have to go through the slides and understand. But at least you do it now and you don't do it later. At the same time, guys, let me open a parenthesis and tell you that it's very important, and it's actually optimizing that you follow or you study during the course. Not because I have any particular interest in the fact that you study or you don't study, just because it's mostly energy efficient. So if after every lesson you take this hour to fix the material, to understand or to go through the slides and to have the questions on the spot, then everything else becomes more fluid. If you ignore everything and you end up at the end of the journey, and then you want to study and to do things, then everything becomes much harder, because the cumulative time that you spend is much higher. So I'm talking to you as a colleague in terms of energy saving actions, not in terms of I want you to study. All right, that's not my interest. I would like you to have fun and to know the things without studying. Closed parenthesis. Then we have done our fantastic ICP, and we might also want to connect our findings on the uncertainty, because this ICP also brings some issue in the uncertainty that we have dealt with in the previous lesson. And we say, okay, now assuming that I work on the manifold, my problem is described on the manifold, I have done all this nice box plussing, box minusing, and so on, and I want to determine in the end the uncertainty of my solution. I mean, the game is actually now that what the manifold formulation will return you is a probability distribution over the perturbation. A probability distribution over the perturbation vector. We have already seen before that that H was the information matrix of the perturbation around the optimum. Okay? And this comes from the previous lesson. And then by observing that we just did a domain change in order to obtain the covariance matrix at the in the domain of the manifold, all we need to do is to apply first order error propagation, or to map basically this covariance matrix in a new space. What is the new space? The new space will be the space of the manifold, and the mapping will occur through a chart centered around the current optimum. Okay, so we have, this is a random variable, this is a function of a random variable, all of it, and what we want to do is to obtain a Gaussian approximation of this random variable, which is obtained by applying this function to this object over here. We recall that the optimum stays fixed during the optimization. Like after we converge, the optimum is just a constant for us. Okay, so we could see this function here as a generic function gx, just to denote that, okay, this x here is a constant that plays a role of delta x. Now, if I give you a function and I tell you, hey, this object here has a Gaussian distribution, I'm sure that you will find a way to determine the parameter of the Gaussian distribution of the output of this function. Gaussian approximation of the output of this function. And to do this, as always, we have our toolbox, and we use the famous tools on first order error propagation. First order error propagation, also called linearization, we take the function gx of delta x, which is here exploded into its definition. We derive it with respect to delta x equal to 0, and then we calculate a normal distribution whose mean is x star, because the optimum doesn't move, and whose covariance matrix is obtained by projecting the covariance matrix through the Jacobian of the transfer function, which is just a box plus. And this is standard, well-known things that stem from the Gaussian manipulation. And alternatively, if you want to be fancier, you could compute the uncentered transform, so the sigma points out of delta xi, and then project each of these sigma points through this capital Xi. And then in this way you will have a Gaussian distribution projected into the manifold space around the optimum. And this is, I believe, quite straightforward. No? So you have a distribution on the perturbation, and then you want to apply it to a specific point, then you take the distribution and you use a transfer function, which is the box plus, to map these parameters into another parameter set. Okay? Now, so far so good. There's a hidden thing in the least square formulation that I've proposed you. In the program, because it was a program, in the algorithm that we have seen, which encoded the variant of least squares, you had, observe well, you had that the measurements were assumed to live in a manifold, right? And here I have an omega, which is an information matrix, that is not consistent with the manifold, right? Because imagine that this is a transformation matrix, and this will be a 6D vector. Well, the two things don't match. So this is a transformation matrix, and this will be a 6x6 object. How do I multiply? There is a mismatch between these two quantities. In fact, here there is a box minus whose goal is to remap both this quantity and this quantity into an Euclidean perturbation that then is conformant to the information matrix. Okay? But what if, for some weird reason, I have a manifold description which is minimal, and I have a covariance matrix which is attached to this manifold description of the measurement, right? Like, so to picture it, imagine that I have a covariance matrix on Zi, capital Zi, or an information matrix on capital Zi. So what can I do in this case? Well, first of all, I start writing down my error function. My error function, and I explode it by putting in it the correct box minus, so the full definition. Now, recall that in what I was describing that the covariance matrix or the information matrix is attached to this object. Okay? If this becomes the random variable, so if I can't do this fancy mean shift that I do usually when I have the regular minus, there is a dimension mismatch, because then this covariance matrix of Z will not be conformant in dimensions with the perturbation E. So I have to invent something. Well, once again, I could describe the error as a Gaussian distribution, and I could calculate the parameters of this new Gaussian distribution, this omega that I call X because it's an omega centered in X, starting from a Gaussian distribution on Z. I can just say that this error will have a certain mean, which is equal to the mean calculated by subtracting the prediction to the measurement with the box minus, and a certain covariance matrix whose dimension should be conformant with the dimension of the perturbation on the measurement, so E. Okay? What can I do? Well, guess what? As always, I can do first order error propagation. So, how? I know that I have my measurement expressed in a manifold through a certain normal distribution on a complicated space Z, and an information matrix omega on this complicated space. Okay? Then I could define the variation of the error function as a function of Z, right? Because this time Z, this object over here, is my random variable. and no one prevents me to do so. Of course, if this is a matrix, this object here will be a tensor or something lifted, but in general, I can always compute the components of this derivative, and then arrange them in a space in a way I please, such that the operations are consistent. So I just take this fantastic function and I derive it with respect to the linearization point. The linearization point at this point will be the mean, or will be the measurement, z with I, my actual measurement. And this gives me a certain Jacobian. Then after I have the Jacobian, I can, as always, do first order error propagation in order to determine, to map the covariance matrix expressed in the manifold into a covariance matrix expressed in the error space, just by doing J omega J transposed. The mean stays as always the mean of the error, because I'm operating on Z. Okay, this is one way. The other way, simpler, or the other fancy way is like, okay, I do error propagation, I sample a set of points from this omega with I, and thus from sigma with I, then I have a set of these sigma points, I project these sigma points through my error function, which is this object over here, and then I reconstruct the covariance matrix accordingly. Okay? Then we can end up with a final and closing formulation of least squares with this additional step, which is how to project the covariance if your measurement space is non-Euclidean. So we start, it's always minimum variation from the previous algorithm. We start by clearing H and B. For each measurement we compute the error, we compute the Jacobian. This time the Jacobian is evaluated in, so it's calculated with respect to the perturbation, and the perturbation evaluated in 0. Then we calculate the transfer for the Jacobian of the error function with respect to the measurement in order to project the covariance matrix of the measurement into the error space. We do this projection. Notice that this Jacobian here depends on the linearization point. So in this case, we might have to rotate the covariances or to change the covariance. The effective covariances of our ICP will be varied during the iterations. Okay. And then we calculate our final contribution H and B by using the manipulated covariance according to the usual formulas that we know. Okay, this looks terrible. Okay, but that's the worst case that can happen. There's an alternative that might rescue your existence, which is when which is most often the case, which is when the covariances or the information matrices are expressed in the chart of the measurement. So that is, assuming that I see there an object, in order to describe the error, I describe the error not on the parameter space of this sphere, this plane or this thing, but I describe the error as in the space of the perturbations around the measurements. Okay? So, if I do so, and I describe the perturbations in such a way, well, then I live better because basically we don't need to remap the covariance all the time, because our covariance or information matrix is computed once and stays attached to the chart. Okay? And we can then conduct our optimization like by using this algorithm over here, which was the first version of least squares, manifold least squares that we have seen, and this version is actually the version which is actually used. Now, I know it's a lot to take with this lesson because it's a core aspect of the course. What we could do if this is not the case is that we could express so in case we have, for some weird reason, the designer of our algorithm or our input gives us the measurements on the manifold, we could do a trick and we could map these measurements only once, basically, by projecting the covariance of the measurement on the chart on the manifold onto a measurement onto the perturbation space. Okay, this we can do it only once, and this is more or less the final version, which is the same as before, and we highlighted omega z to omega delta z to explain, hey, this omega here, in order to make everything consistent, must be an omega expressed in the chart. Okay. This is the conclusion of this lesson, that it's a lot to take, I believe. The idea is that from now on we will always operate on manifolds, and this brings us advantages, because sometimes, even if it looks a little bit more worky, sometimes a lot of things becomes constant, and the calculations becomes easier. Recall the case of ICP, where in the end we had to compute the derivative of a rotation matrix in a constant point, and the constant point was 0. The idea and the mechanism of the manifolds can be imagined like that. Can we imagine that we have an input problem in whose state space is rather complicated, and at each iteration what we do is that we change our origin and we relinearize the problem in an Euclidean space around that particular origin. Because this is the mechanism of the recalculating the chart, which is implicitly done by the box plus operator. So you can imagine that your linearization point on the manifold moves at each iteration, because you update it with a box plus. But then at each iteration what you do is to calculate an Euclidean approximation of your problem at the origin. And this leaves you constantly away from singularities, or as far as possible from singularities. Okay. So now, if you have questions, I will now fire a Zoom session, because I believe that there will be quite some questions. Or alternatively, if you want, I will quickly go through the slides of Friday. You choose. Just write down on the chat what you want. Do you want question session or a recap of the lesson I've done Friday? I'll go to get a glass of water and you write. Okay. Okay. So the majority votes for a recap, and we go for the recap. I mean, this is a record lesson. I've done 4. I will be doing 4 packs of slides. For Tiziano, this is a record. Because he always makes fun of me that I burned the slides. I think we started with this, right? Now, very quick recap. Last time we were talking about 3D point registration. So like we were lifting our ICP to move to 3D, right? So now ICP is, we have seen it up to the nausea, I think. So I will quite skip with these things. And then I recall that this version, this part of the lesson, did not yet assume that we were talking about manifolds, okay? Because it was done before. So in the next episode on Friday, we will see the manifold version. But the methodology requires me to qualify the state, and in this case, I know that the state is an SE3 object. So it's ICP in 3D. And I parameterize it through a translation vector and 3 angles, right? Alpha x, alpha y, alpha z, that are the 3 rotations along the 3 axes. The measurements are points in R3, and the prediction function is exactly the same as in 2D, only that it is lifted in 3D. I have the rotation matrix constructed along the angular components multiplied by the point plus the translation vector, right? And this gives me the point in the reference frame, the word point in the reference frame of the robot. Now, small recap on rotation matrices. Well, there are a gazillion way of composing rotation matrices on angles. Actually, you could swap these 3 things as you want, but we will stick to this because you remember much easier x, y, and z. So a rotation matrix is the product of 3 rotation matrices, alpha x, alpha y, and alpha z, Rx of alpha x, Ry of alpha y, and Rz of alpha z, where we have a small lookup of the rotations. We have Rx, Ry, and Rz, which are like what you have seen in probabilistic robotics, rotation along the x-axis, along the y-axis, and along the z-axis. If we have these 3 rotations, we can also compute, just because they might come handy, the 3 derivatives, right, like of the rotation. So from this comes this, from this comes this, and from this comes this. Okay? Having written my rotation matrix in this form, and then I could go back and expand this formula here by highlighting the role of the rotation matrices. The Jacobian of ICP will be 3 by 6, in 3D will be 3 by 6, because measurement is big 3 and the state is big 6. The first part will be the derivative of h with respect to the translation part, which, if you recall, the derivative of this object with respect to t is the identity, t is as dimension 3, so the corresponding block will be 3 by 3, and I put an I here. And then I will have 3 columns, which is the derivative of the prediction with respect to alpha x, alpha y, and alpha z. To calculate that, I just expand the definition of the rotation. Expanding the translational component disappears. If I wouldn't derive this contribution, I will have Rx, Ry, and Rz times pi. Given that I derive, in this case, with respect to alpha x, I just substitute this Rx with R prime x, and then the rest stays consistent. And so, in this way, I determine this vector. This is consistently a 3 vector. I do the same for the second object, and I do the same for the third object. Having done that, I also demonstrated, but this I will not do it now. I will like how the program looks like. This is quite straightforward. You extract the 3 transform. So x the program looks like. Here you see the error and Jacobian, the famous function which is at the root of my example implementation of ICP, where given a transform X which is expressed as the that6 vector, a point P 3D and a measurement Z, calculates the error and the Jacobian. First thing first, you extract the 3 rotation matrices from the component, the 4th, 5th, and 6th component of the state, which will be Rx, Ry, Rz, and given that they will come in handy for the Jacobian, you extract the 3 derivatives of the rotation matrices. You extract also the translation vector. You calculate Z hat, you calculate the error, you calculate the Jacobian following the formulas before, and you are all happy. The iterations are the same thing of ICP in 2D, with one single difference, that the dimension now becomes 6. So the dimension of H, and coherently the dimension of B. If you run it, we do what we typically do for ICP. You spawn a set of points, you compute some measurements from a random location, and then you let it converge. The convergence, in this case, the space has grown. The convergence depends, the behavior of the system depends pretty much from the initial guess, which is the point where you start the optimization. Here you see, if you start from a decent initial guess, the system goes abruptly down, but if you start from an initial guess which is less good, you might have these weird behaviors. So this is the evolution of the chi-square of the ICP during the iterations, and then you see that the error decreases, but then increases again to decrease afterwards. First of all, the error goes down because the problem is quite convex, in a sense that you have a lot of points in this case, and then sooner or later, after tampering a bit, then you go down to the minimum. You also have 6 is very small dimensional as a problem. But still, you might observe that in this case you have this bump of the error. It doesn't go completely down. This is presumably due, because we don't have the manifolds, this is presumably due by the fact that you normalize badly the angle, and then you turn in the opposite direction during the optimization, and then after doing some mistake you come back to the right one. And then we were speaking also about another technique that we called linear relaxation. So linear relaxation is a way to relax the original problem, so to get rid of some constraints that we have on the state variables, by simplifying the problem and rendering it thus linear. I recall you that if my prediction function is in affine form, then I can find the optimum in just one iteration. And this seems to be reasonable to be done in ICP. So the framework of linear relaxation is to relax some constraints on the structure of the state, like for instance that it's a rotation matrix, in order to find a solution to a problem which is easier, even if it has more parameters than the original one, and then after that reconstrain the solution. This, of course, will not find the optimum of the original problem, but might bring you to a decent initial guess. The idea in this case is like to relax the constraint that R is a rotation matrix, if we want to apply linear relaxation to ICP. So like we could talk now, if R is not anymore a rotation matrix, we are left with 12 possible active parameters, which is 3 parameters for the translation and 3 parameters for the vectors of the rotation matrix. Having said so, we can construct a 12-dimensional vector which is consisting of the 3, these are the rows of the rotation matrix, which we put in column just like to have a 12 vector. So this is the first row, second row, third row, and this is the translation vector. Like the error function doesn't change, only the fact that the state has now 12 dimension changes. The error function will be then the same as before, where you have the rotation matrix multiplied by the point plus the translation. And so you re-express the rotation matrix by the 3 vectors, one stacked on top to the other, plus the translation. Now, if you massage this formula over here, and you basically flip P and R, you could rewrite this product in this way. So consider that this component, this object here is the dot product between the first vector of the rotation matrix and the point. This will be the first component of this vector. This is the second dot product, and this is the other dot product. If you transpose both members, you could rewrite this part of the sum into this form over here, where we see the three rotation vectors stacked onto each other, and the matrix which depends only on the point, which we call Mi, which is the point repeated 3 times. So this is 9 by 3. So 3 rows, 9 columns. It's cool because if we derive this function over here, we notice that it doesn't depend nor on R nor on T. Okay, because this R will become 1 and T become the identity. This means that the Jacobian doesn't change during the iterations, and we find the solution in just one step. Accordingly, like basically the Jacobians will become, or the Jacobian of this object here with respect to R will become just Mi, and with respect to T will become the identity. And this is what we find in the next slide. So we rewrite the error function highlighting the role of M, and so and the role of and the Jacobian then becomes and the error function becomes the following, and the derivative of this function will become M for the components that are related to the rotation part, and T for the components that are related to T. Now we know that the problem will be by realizing that the Jacobian doesn't change, we know that we can find the optimum in just one iteration, and also that the initial guess doesn't matter in this case, and so it makes a lot of sense to select the identity as an initial transform in this case, because just like bang to the optimum. And then by doing the products of j omega j, we find this formulation for H and B, and then in one go we can go to the solution. There is one little problem of the linear relaxation mechanism, is that in fact we will find a solution, but we will find a solution that relaxes the constraint that we have a rotation matrix. So like we have to think about that if our problem would be noise free, we would find a solution which is very close to, which is a rotation matrix, but we have noise, and then in the end the noise gets absorbed in the free component of the rotation of this R matrix, which is not a rotation matrix, that we added into the vector. And so in order to come back to a reasonable system, what we could do is to do the pictures and find the closest approximation of a rotation matrix to the input matrix, to the matrix constructed by putting these three vectors. And to this extent, we use the SVD decomposition that takes a matrix A and decomposes in two orthonormal matrices U and V and a diagonal matrix D. Now, if D is an identity, then we have found a perfect approximation of a rotation matrix, but in general D is not an identity. And so what typically is done is to look at D, whose components will be as far off as from the identity as the worst is our approximation. If it is too different from the identity, we know that what we have is not a valid solution, because we have too much noise and linear relaxation didn't bring us something good. But if it is close to the identity, we say, okay, I don't care. I just like get rid of D. I force it to be the identity, and I recover the rotation matrix R. This is the matrix returned by the linear least squares, by multiplying the two orthonormal matrices that I know to be another orthonormal matrix. Because if I set D to the identity, I just go back to the space of the orthonormal matrices. This is quite decent, because so this might be inviting if you can do it, but it works if don't have many bad correspondences and the error, meaning the noise, is small. if the noise is too big, as I mentioned already, well, basically then you are incorporating, you're decreasing the error more than in the other solution, because you have more degrees of freedom that you can use to lower the error, but you can you are at the same time obtaining something which is far from what it should be, because you're violating any constraints. So normally after linear relaxation, you can boost your ICP with linear relaxation and then do a couple of iterations of nonlinear least squares to enforce the constraints and stick to the optimum. Okay, this was lesson 1. How many slides? 17 slides in 10 minutes. It's a record. Let's see then the robust estimators. This is a little bit more rich. Are you still alive? Alive? Vivi? No. Oops. Okay. Okay. Do you want to have question time or the recap on robust kernels? I can also talk faster, but I won't. Do you want question time or a recap or robust kernels? Okay. Oh. Ah. Okay. Okay, let's go with a recap of the robust estimators. Now, guys, I'm going fast because you have the other lesson. This is just like to bridge you, in case, repeating things is never too bad. Okay, now, robust kernels. Now we know that basically Gauss-Newton, what Gauss-Newton does is to find the minimum of a set of error terms, where each error term is obtained by what we call the omega L2 norm of a vector. So the omega L2 norm of a vector is defined in the following way. I have a vector V, I have a symmetric positive definite or semi-positive definite matrix omega, and this is the omega L2 norm. So the vector multiplied by transpose, multiplied by omega, multiplied by V. Clearly, if omega is the identity, we end up in what we call the L2 norm, which is just like the squared Euclidean length of the vector. Okay? And this is like what we do minimize. What we do minimize is the sum of the squared omega, the omega L2 norm of the error vectors. This is what we minimize with Gauss-Newton. Okay. Now there's some considerations that we can do. We can instead of talking about omega norm, we can always talk about normal L2 norm. So with omega set to the identity, if we slightly massage a vector. Like remember that we typically have an information matrix attached to our measurements, which is this omega. Information matrix is symmetric positive definite, so accordingly it contains it can be subject to Cholesky decomposition, and so like in order to calculate, let's say this way, this L matrix constitutes a mapping between the pure error space and error space which is normalized by omega. Because if you regard this as being your error, and if you take your error and you multiply it by L, this L here does nothing else than projecting this error into a space that absorbs the contribution of the information matrix omega. Okay? And this is in the end purely a linear transform of the object. So in case there are certain implementations that do this explicitly, because multiplying omega twice, because L is maybe sparse or so it's quicker to do this calculation rather than V transpose omega V, because then in the end this operation, the operation of calculating the omega norm, the omega L2 norm of V, boils down to the operation of calculating the norm of V prime, which in the end requires to calculate a dot product and not a product between a matrix and a vector. But this was just for completeness. So there is a relation between the omega norm and the omega L2 norm and the plane L2 norm, and this relation is just like through a matrix L that maps one space into the other. It's like L stretches the space in a way that the distances are conformant with omega. This was the omega norm, and then the omega norm grows with the length of the vector, because you have a square there, right? Like you have a vector multiplied by itself. When you compute the dot product of a vector by itself, each term comes squared, right? So like the distance or the cost will grow quadratically with the magnitude of the individual components. There's another norm which is called the L1 norm, which is nothing else than the square root of the omega norm. Before you had a 2 here, you don't have a 2. If you remove the 2, then you take the root of the L2 norm and you have the L1 norm. Benefit of the L1 norm is that, well, it doesn't overweight quadratically. If I have one point which is much more wrong than the others, this one point, this one error will drag my solution a lot because it has a quadratic strength, while all other points were happy where they were before, and a potentially better solution would have been to ignore this one bad point, right? Or to lessen it less, or to lessen it more, or to not consider its contribution as quadratical. So we might have some benefit in using the L1 norm. The problem with this is that we forget the Gaussian universe, like basically, because all what we have seen, especially regarding uncertainty, if we would be using the L1 norm, would be lost. But we don't care at the moment, at least for what concerns to calculating the optimum. Then after the optimum, we can still trigger the quadratic norm. So like then we have to reason a little bit about the outliers. So there are many cases, or it's actually typical that the measurements, they come from sensors and they come from algorithms. And the algorithms, they do not know the perfect data association, nor, or sometimes the error is too much that makes you committing association errors. So like the game of this tool, or this part of the lesson, was to deal with outliers. Like to think that there might be measurements in my set, in my Z, that are not good, that I should get rid of, okay? Because they are coming from error somewhere else. There are two ways of dealing with errors. One is to use consensus schemes, and the other one is to use M-estimators, which is what we will talk now. These estimators work assuming that you are in a reasonably good configuration, and then from that point on, just by looking at your configuration, you can tell which measurements are bad. Okay, now we introduce the M-estimators. Like the game of an M-estimator is to change our cost function to a new cost function, where basically we are minimizing the sum of what we call robustified. Now this is a function rho, which is monotonically increasing, and the argument of this function is the L1 norm of my error, which we will call UI. Okay, so This is the game of the M estimators. And we want to find out if we can massage the M estimator in a way that the Gauss-Newton algorithm in a way that we can embed this thing. Now the game is that you can, by modulating this function rho here, you can change the behavior of your optimizer. Now clearly if you would choose rho as rho of u to be u square, here you will end up in the L2 norm, and you will end up in the plane case that we were talking before. Here is a slide of common cost function that are used. This is the no cost function, so the L2 norm, the L1, the truncated that behaves like this but then chops it, and so on and so forth. Now, how do we would like, our task now is to modify the Gauss-Newton algorithm so that we can somehow approximate or embed these robust cost functions that we know will help us in dealing with outliers. We recall that to minimize a function, we need to take its derivative and set it to 0, which is what we always did, right? Okay. So now my talk will start massaging the derivatives and calculating the derivative of the robustified L1 norm function and compare it with the derivative of the L2 norm that we were always working with during our Gaussian in our Gauss-Newton implementation. Now it's quite straightforward that the derivative of the L2 norm is this one, because this is the derivative of the square, which is 2e. Then there is this, you have to think it about e transpose omega e, and so like then the derivative will become twice e transpose x omega, and then the derivative of the argument. Just if you compute it by hand, it will result to be quite obvious. Now this is the derivative of the L2 norm. Okay. Oh, like if you have the derivative of f square, you have 2f times f prime. Only that here in between you have an omega that multiplies the gain. Now, having written the derivative of the L2, we can write the derivative of the L1. Well, this is if you have the derivative of the square root of something to the square, then this derivative will become 1 divided by twice the derivative of the square root of the object, which multiplies the derivative of the argument. Now, the inner part is the L2 norm. On the bottom floor, you're going to find the square root, like the square root of the square, so which we could write just as the L1 norm, and at the end you retrieve that there is the usual derivative of the L2 norm, with the difference that we can drop the 2 here and here. By renaming the L1 norm to u of x, we can replace this term here. Yes, by renaming the term e of x, so the L1 norm of e of x by u of x to denote it's a scalar, we go from this floor to this floor. Okay, this one here was just the explosion of the derivative of the L2 norm that in the bottom floor re-became the implosion of its definition. Okay, now this is the derivative of the L1 norm. All happy that we can compute the derivative of the L1 norm as by taking the L2 norm and dividing it by the norm. Now, if we introduce robustifiers, well, we recall that the robustifiers introduce another level of derivation in our chain. So the derivative of the robustified function will be the derivative of the robustifier evaluated in u multiplied by the derivative of u, which in the end will result in the following formulation. This is the derivative of the argument, and this is the derivative of the cost function. By setting the cost function, the robust cost function, by setting all this block over here to gamma, so all this gigantic papone here, gigantic soup here to gamma, we could more compactly rewrite this equation as gamma that multiplies the derivative of the squared norm, which is the function that we were minimizing in Gauss-Newton. Okay? So we could rewrite and then we compare the terms side by side. We compare the derivative of the function, the robust cost function, robustified cost function, and we compare the derivative of the non-robustified, of the L2 omega norm. Okay? And we see that these two objects here look quite similar. In particular, here you have a cost term, gamma of x. This is a constant. This is a function of x. Now, calculating effectively this derivative and casting an optimization system would be a hell. But what we can do is to think that x will gradually converge towards the maximum. And so we could basically use the x at the previous step in order to compute the derivative of the next step. And so, like, in the end, we could replace the norm, we could emulate optimizing this derivative just by taking this term here and immersing and putting it as a constant that changes on the iteration in this derivative over here. As for instance, a factor that multiplies omega. Okay? And this is like basically the game of iterative reweighted least squares. So you start from a clean system, you compute the error and the Jacobian, you compute the norm, the magnitude of the error vector, you compute the gamma term, and then you use this gamma term to massage the information matrix to absorb the behavior of the robust cost function. This works because at the next step you're using the estimate of the previous step. And this concludes basically the second lesson. I have been turbo me. I think we are all baked, so we can close the lesson here if you want, if you don't have questions. I got to get a glass of water because I'm getting corona. Thank you, Barbara. Okay, then we close here. That was destructive. And I will go on a mid-session in case you have questions. Okay? Ciao, ciao.